1,000 degrees Celsius, steel begins to lose its structural integrity. But for a firefighter, this inferno is where they do their most critical work. How does a fabric thinner than a single centimeter stand against temperatures comparable to the surface of the sun?
This chamber allows
The answer
us to
lies
test
deep within
materials
molecular
under
engineering.
Extreme thermal stress.
Today we dive into the science of
real-world
the
fire
Nomex heat
conditions
suit,
safely
a
within the
marvel of
lab.
modern technology designed to keep heroes safe in the heart of the fire. When the flashover occurs, heat radiation attacks with brutal force. Every second counts, and the suit must act as an impenetrable wall against the heat. This isn't just clothing, it is a life support system. It manages heat, moisture, and toxic gases.
This is Nomex fabric.
All while
Watch as
allowing
I
for
apply
extreme
the
physical
direct
movement
flame
and
from
danger.
this gas torch.
Observe this.
As you can see, it
Even
glows
under direct
intensely,
contact with a
but it
high-temperature
simply
gas
will not
flame,
burn.
the fabric does not ignite or melt. It simply resists the energy of the fire. This inherent flame resistance is what separates these technical textiles from anything you would wear in daily life. It is the first line of defense. Behind every rescue mission is a complex manufacturing process that transforms liquid polymer into a shield for the brave who face the unknown. Let us step into the laboratory to see how this extraordinary journey begins, starting at the very foundation of the material's atomic structure. Nomex is a synthetic aramid polymer. Its molecular structure contains aromatic rings that create an incredibly stable and heat-resistant chemical backbone. Unlike cotton, which fuels fire, Nomex molecules carbonize when heated. They form a thick char layer that actually absorbs energy and slows heat transfer. The process begins with a liquid polymer solution. This chemical soup contains all the properties needed to survive the most extreme thermal environments on Earth. This liquid is forced through microscopic spinnerets. As the liquid streams hit a chemical bath, they solidify into continuous, ultra-strong filaments of fire-resistant fiber. These filaments are thinner
Here we see the remarkable
than a human hair,
detail of the Nomex fiber.
but stronger than steel by weight.
The smoothness you observe here
They are
is
bundled
key
together
to its durability and
to create the
performance under
yarn
extreme conditions.
used for weaving. Under the microscope, you can see how perfectly smooth and dense these fibers are. This density prevents oxygen from penetrating the fiber, inhibiting combustion. Strength is just as important as heat resistance. If the fabric tears in a fire, the protection is lost. Every batch is tested for maximum durability. Thousands of these bobbins are prepared, each carrying kilometers of yarn that will soon be woven into a complex, multifunctional fabric matrix. Additional treatments are applied at the fiber stage to ensure the suit can withstand sunlight and chemical exposure without degrading its protective qualities. It feels like normal textile, but it is a high-performance material, born from decades of chemical research and intense safety engineering. Now we move from the chemistry of the fiber to the mechanical art of weaving, where these strands become a wearable shield. Modern looms operate at incredible speeds.
Notice how the vertical fibers
interlacing
weave over
thousands
and
of
under the
Nomex
horizontal
yarns
threads.
into
This
a
intricate
tight,
interlocking mechanism
consistent
is what gives
weave
the fabric its
that can
unique
block
stability and
intense
strength.
thermal energy. We use a specialized ripstop weave. Look at the grid pattern. These reinforced threads prevent small snags from turning into dangerous tears. This structural matrix is designed to remain stable even when the fibers begin to carbonize in extreme heat. maintaining a physical barrier. Precision is key. A single missed thread could create a weak point where heat might penetrate, so every millimeter is monitored by optical sensors. Once woven, the fabric is called the outer shell. It is the most durable layer designed to take the brunt of the physical punishment. Every roll undergoes a rigorous inspection. We look for any inconsistencies in the weave that could compromise the suit's performance during a rescue. We also apply a durable water repellent. A wetsuit is a heavy suit, and water can conduct heat, increasing the risk of steam burns. The scale of this operation is immense.
The outer
Thousands of
canvas
meters
is
are
tough
produced
and
daily
textured,
to
while the inner
outfit fire
lining
departments
is this
across the globe
smooth,
with the best
lightweight
protection.
quilted nylon.
Laser cutting ensures that every piece of the suit is identical and fits perfectly, which is essential for maintaining the integrity of the heat seals. But the outer shell is only one part of the story. To truly survive 1,000 degrees, we need a sophisticated multi-layer defense system. The heat suit is a sandwich of 3 distinct layers, each with a specific mission to protect the firefighter from different types of hazards. The outer shell provides mechanical strength and resists direct flame. It's the armor that protects the more delicate internal layers from damage. Next is the moisture barrier. This incredible membrane is made of PTFE. It blocks liquid water and chemicals, but allows hot sweat vapor to escape. This breathability is life-saving. Without it, the firefighter would quickly overheat from their own body heat, leading to heat stroke within minutes. It also acts as a shield against hazardous liquids like gasoline or toxic chemicals, often found at industrial fire sites, keeping the skin safe. The final layer is the thermal liner. This is the most critical part for blocking heat. It uses quilted air pockets to provide insulation. Air is one of the best insulators. By trapping air in these Nomex felt layers, we create a barrier that heat simply cannot penetrate easily.
3-layer heat-resistant
The liner
glove.
must remain lofty.
It allows
If
me
it compresses
to touch this
and the insulation value
800-degree hot
drops,
plate without feeling
that's why we
any
use
warmth.
high-tech non-woven Nomex batting inside the quilt. Together, these 3 layers create a thermal gradient. Even if the outside is 1,000 degrees, the inside stays at a survivable temperature for several minutes. It's a miracle of physics. We are managing radiation, convection, and conduction all at once within a flexible, wearable garment system. The challenge now is to assemble these layers into a suit without creating any thermal bridges where heat could leak through the seams. Every stitch is made with Kevlar or Nomex thread. Using standard polyester thread would be a disaster, as it would melt and the suit would fall apart. We seal the seams of the moisture barrier with high-temperature tape. This ensures that the suit is 100% liquid tight, even at the joints. Knees and elbows are reinforced with abrasion-resistant materials. Firefighters spend a lot of time crawling, so these areas must be incredibly tough. Reflective trim is added for visibility and smoke. These strips are also made of heat-resistant materials so they don't melt or peel off in the fire. The closure system uses heavy-duty brass zippers and flame-resistant hook and loop fasteners. A double flap system prevents heat from entering through the zipper. Every opening, from the neck, egg to the wrists, is designed with a seal to prevent hot air or burning debris from getting inside the suit. The design must allow for maximum mobility. Ergonomic patterns ensure that the firefighter can climb, reach, and carry heavy equipment without restriction. A completed suit is a work of art and engineering. But before it can be trusted in the field,
The
it must
thermal
face
readout
the
on the
ultimate
left
test.
leg is exceeding tolerance.
Welcome to the Flashover Lab.
Adjusting the parameters
This
now.
is where we simulate
The
the
structural
most dangerous
integrity
moment
seems
a
stable.
firefighter can face. A total room fire. This mannequin is equipped with over 100 sensors that measure how much heat reaches the skin during a fire simulation. The computers will calculate the probability
chamber
of
is
second and third degree
secure.
burns based on the
Beginning
heat
the
data collected
activation
during the 10-second
sequence.
blast. Everything is ready. The suit is zipped tight, the sensors are calibrated, and the gas lines are primed for a high-intensity thermal attack. The countdown begins. In a few seconds, the temperature inside that room will jump from ambient to nearly 1,000 degrees. Ignition. The fire roars with terrifying power. This is the flashover test. The suit is now being pounded by pure thermal energy from every angle. Notice how the fabric reacts. It doesn't melt. It carbonizes and thickens, creating an even better insulating barrier. As the heat increases, 10 seconds. In a real fire, this is the window of survival. The suit must hold its shape and its protection for this entire duration. The fire is out. Now we wait for the sensors to tell the story of what happened beneath those layers of Nomex and Kevlar. At first glance, the suit is charred, but look
Despite
closer.
the intense
There are no
heat
holes, the structure is
exposure, once
perfect,
we remove
the internal layers are
sacrificial
still
layer,
pristine.
The white
The
moisture
data is
barrier
in.
underneath
The
remains
internal skin
perfectly
temperature remained
intact.
below the threshold for serious burns. The suit has successfully saved a life today. The sacrificial charring of the outer shell did its job. It absorbed the thermal shock, protecting the critical moisture barrier and thermal liner inside. Even after such a brutal test, the suit maintains its integrity.
From the classic black tuxedo
This is the
to
reliability
sophisticated
required by
navy
fire
blue,
departments around the
and
world.
even our exclusive gold
Post-burn
designs,
testing
we
ensures
have the perfect
material
suit for
hasn't
your
become
next
brittle.
event.
It must remain flexible enough for a firefighter to escape the building after the flashover.
This device.
Whether it is
It makes
an
life
industrial fire,
so much easier.
an aircraft rescue, or a structural collapse, there is a specific configuration of this technology for every threat. It is humbling to realize that thousands of hours of chemistry and engineering go into every single garment we produce in this facility. For the men and women who wear this armor, it is the only thing standing between them and a 1,000-degree death. It is their shield. From the atomic bonds of polymer rings to the final double-stitched seam, the journey of a heat suit is one of uncompromising precision. We often focus on the bravery of the person, but today we celebrate the engineering that makes that bravery possible in extreme conditions.
Here, human ingenuity
Every suit
meets
carries a
advanced
promise.
automation.
A promise that no
Creating
matter
the
how
vital
hot the fire
technology
gets,
that
the science
drives
inside
our
will
world
fight to
forward.
keep you cool. As technology advances, we are looking at even thinner, lighter materials that can withstand even higher temperatures for longer periods of time. The future of firefighting gear is smart, integrating electronics with advanced textiles to provide a complete picture of a hero's health in real time. Because as long as there are fires to be fought, there will be engineers working to build a better, stronger, and safer shield. And protecting our heroes is not just a job, it is a mission. Every life saved is a testament to the power of human ingenuity and science. Thank you for joining us on this journey through the world of high-heat engineering. Science doesn't just create clothes, it creates legends. engineering for life, protecting those who protect us. This is the story of the 1000-degree heat suit. Stay safe, stay protected.